After decades in deep space, Voyager has just transmitted a signal that's left NASA scientists stunned and deeply unsettled. The message is real, it's recent, and no one can explain what caused it. Our beautiful blue planet has only one moon, and it is a battered and sorry-looking thing. It has obviously been impacted many times, smashed into with enormous force to leave craters so big that we can see them by just looking up into the night sky. But this may not have been a slow siege, not a gradual bombardment by the cosmos on the moon's scarred surface. Rather, it was a blitzkrieg. Evidence from the moon's surface suggests that these impacts may have all happened within a very cosmologically short period of time. A surge of falling meteorites that swept across the moon in an apocalyptic rain. Scientists named this event the Late Heavy Bombardment, and while it is a theory, it would have been a truly devastating period of history, with some surprising consequences. It may be the reason we're here today at all, but if it truly happened, what caused it? And if the moon was so scarred, how did the Earth avoid the same fate? I'm Alex McColgan, and you're watching Astrum. Join me today as we journey back in time, for billion years into the past, to unravel a story of chaos around our newly formed sun, as its planets settled down into the orbits that we are now familiar with. When the Apollo astronauts came home from the moon, the rocks they brought with them told a surprising story. The astronauts had brought home samples containing impact melt, rocks that had superheated into magma due to being hit by a meteorite, which had later gradually cooled back into solid form. But while the Apollo team had collected these reconstituted rocks from different areas and craters on the near side of the moon, almost all of them were dated to around 4.1 to 3.8 billion years ago, with very few showing older impacts. The implication? For some reason, during this period of roughly 500 million years, there was an abnormal spike in falling meteorites that crashed into our moon. This idea came to be known as the Late Heavy Bombardment. This idea is controversial, and not everyone agrees that it happened that way. Such is the nature of scientific debate built on limited evidence. We don't get to the moon very often to collect more samples, so it's hard to tell if some process has been muddying the waters. But if the Late Heavy Bombardment happened, what could have caused it? To answer that, we need to consider conditions back at the dawn of our solar system. It is a well-known idea that our solar system was formed from an accreting disk of intergalactic dust and matter 4.6 billion years ago, circling around a gravitational center that would later house the sun. Gravitational disturbances caused some of this dust to bunch together, and once that happened, each larger ball of matter found itself snowballing in size. Larger clumps had larger gravitational pull, which pulled in more mass to grow the clumps. At this period in history, the vast spinning disk of matter from which our whole solar system was created had clumped together into planetesimals. These were further attracted to each other, crashing together to form the planets we know today. Within a mere 100 million years, this process of planetary accretion had gathered up almost all the material nearer to the Sun to form what we call the terrestrial planets: Mercury, Venus, Earth, and Mars. One of these impacts formed our moon, flinging a huge lump of molten rock into space, which formed into a sphere and cooled, and has remained in orbit around our planet ever since. There would still be some isolated leftovers between these planets. Some are still out there today, like the 1.5 million floating asteroids orbiting the Sun between Mars and Jupiter, but this process had pretty much cleared out everything in the inner solar system. But under this idea, you might expect to have more impacts at the beginning, but fewer and fewer impacts as time went on, not a sudden spike. So why could there have been a surge in impacts 4.1 billion years ago that gave our moon such a beating? That has created quite a puzzle for scientists, although some now think they may have solved it. The finger of suspicion points towards Jupiter, the largest planet in our solar system with more than 2.5 times the mass of all the other planets combined, and the first to form, along with Saturn, as our solar system took shape. If you would like to learn more about Jupiter and its influence on our solar system, check out this video. The suspected behavior of Jupiter is key to explaining the observations that have led to the proposal of the Late Heavy Bombardment theory. Jupiter is not thought to have always orbited at a distance of 768 million kilometers from the Sun. Initially, Jupiter moved inward towards the Sun, reaching roughly where Mars orbits now. Mars and the other inner planets didn't yet exist at that point. only to then change direction and pull away again. All of this possibly happened within just hundreds of thousands to a few million years. What made Jupiter behave like this? The short answer is its relationship with Saturn. When Jupiter formed, there was still a huge amount of gas swirling around our developing sunday. This gas dragged Jupiter along towards the center of the newly forming solar system. Once Saturn had formed, it also joined this death ride towards the Sun. However, the two new planets bonded as their gravities combined, and the sudden tug of Saturn behind it was enough to arrest Jupiter's grand procession towards the solar system's inner territory and to gently pull it back to the orbit we see it at today. But this procession was not without impact, quite literally. Our asteroid belt, with its 1 to 2 million asteroids, potentially only represents less than 1% of the matter that used to be there. So when Jupiter came sweeping through, with its massive, far-reaching gravitational pull, a lot of orbits became disrupted, and many of those objects started to fall inward. Two types of asteroids were brought into this process, from both the inner and outer solar system. This fact becomes quite important later. Not all asteroids are the same, and you may be familiar with the terms S-type and C-type asteroids. S-type asteroids are the stony asteroids from the inner solar system, mainly made up from silicate materials and nickel iron. They are drier because they come from closer to the Sun. C-type asteroids, the chondrite asteroids, are the most common and are among the most ancient objects in our solar system. They come from the outer asteroid belts, and they contain much larger amounts of something that would later prove to be crucial to our planet: water. And all of these asteroids began to fall through the patch of space our planet was orbiting. So, to answer my initial question of how the Earth avoided all these asteroids when the Moon was constantly, apocalyptically bombarded, it didn't. The timing of this, as far as our own planet is concerned, was crucial. By then, the surface of the Earth had cooled to form a more stable crust, what we know as the lithosphere today. This insulated anything above from the enormous heat of the magma below. The magma near the surface was much hotter than it is today, around 1,600 degrees Celsius, and it was much more liquid. Heavier elements, especially iron, had sunk towards the central core, leaving the lighter elements and minerals at the surface. As the asteroids rained down onto the surface, they brought with them a whole range of elements and minerals that would remain as part of this surface layer. It is now thought that many of the important deposits we find at the surface today, ores and metals such as lead, nickel, copper, and gold, were brought there in this way. More important than valuable metals, however, was the arrival of water. Vast amounts of water. Had all of this water arrived earlier, when the surface of our planet was hotter and less able to maintain an atmosphere, much or all of this water would have escaped back into space, possibly leaving the planet in arid desert like Mars and the Moon. Surrounding Earth during the bombarding chaos 4 billion years ago was a toxic atmosphere of methane and ammonia covering an unstable but solidifying surface of basalt-type rock, dark gray, almost black in color, and with brightly glowing lava erupting through faults where it was shattered by the incoming hailstorm of asteroids. Steaming oceans of water were forming, helping to further cool the developing surface. A true vision of hellfire and brimstone. It is partly because of this churning nature of the surface, floating on liquid magma, that today we see no trace of the craters left by these impacts. The forming lithosphere was fractured into many small tectonic plates that moved around and recycled themselves much faster than they do today, and no trace of these early rocks remains. The oldest surviving rock formations on our planet roughly mark the end of the Hadean period, and by this time, this intense bombardment of our planet had likely come to an end. The end of the Hadean era also marks the beginning of a new development in our planet's fascinating history, the story of life. It has long been debated how the very beginnings of life may have evolved on Earth. Key building blocks would have been needed: hydrocarbons and other complex molecules. What conditions could have led to the origins of this organic molecular soup? Interestingly, while there is debate over the reality of the late heavy bombardment, this theory does help to answer this vital question. It is now known that all 5 of the essential building blocks of DNA and RNA exist in space and have been found on meteorites. But while the meteorites that we see today burning up in the night sky as they enter our atmosphere could never bring anything as delicate as these molecules to the surface of our planet, they would burn away to nothing before even reaching the stratosphere. But when much larger objects from space were raining water and ice onto our newly formed surface, it is certainly possible that they seeded the Earth with some of the right ingredients that made life viable. There is compelling evidence that life began at the very time when this bombardment was ending and new oceans had formed. Finding the answers to many of these questions is almost impossible on Earth because so little remains from this time. This is why scientists are so keen to study clues that may still exist on the Moon. The reason why this evidence is so well preserved on the Moon is that, unlike Earth, the surface of our Moon was already quite stable, without the churning and recycling of the surface that occurred here on Earth at that time, so the craters remain intact. Also, the surface of the Moon is not being constantly eroded by weathering. There are no seas to grind it down, no wind and acid rain to wear away the rock. The dust that covers the surface is pulverized rock that remains undisturbed following those dramatic impacts from billions of years ago. There are craters on our planet's surface, such as the Barringer crater in Arizona, USA, but that dates only from 50,000 years ago. Of the late heavy bombardment era craters themselves, there is nothing visible at the present time. If such craters do survive somewhere on our planet that have not been completely eroded away, they could be buried under later sediments or lava flows, and we may never find them. We've been able to make progress in our understanding of this era thanks to the astonishing 382 kilograms of moon surface rock brought back to Earth from the Apollo missions. Radiometric dating of these rock samples indicated that they were last molten during a narrow period of time around 3.9 billion years ago, consistent with when we believe that Earth and the other inner planets were being bombarded by asteroids. Those large craters you see on the Moon are where asteroids have impacted the surface, and then lava has flowed out, forming those characteristic smooth craters that we can see on clear nights. Not everybody agrees, however, and as more refined analytic techniques have developed over time, questions have been raised about the timescale and duration of this period of asteroid activity. Some dating inconsistencies suggest that the craters may have formed over a much longer period of time, tailing off from the planetary accretion that formed the terrestrial planets, rather than a more concentrated period of activity. The sample materials that scientists have available from the Apollo missions are still limited as they stem from just a few carefully selected locations. More samples from future missions will hopefully resolve some of these controversies, and the NASA Artemis missions could see another landing on the surface of the Moon as early as 2026. I can't wait to see what new discoveries this could bring. The late heavy bombardment theory may not be a perfect explanation, but it tells a convincing story that fits with our observations of the Moon and of the parts of our planet's surface that we have explored so far. And it provides some possible answers to the question of how such a vast amount of water came to exist on the surface of what had once been a molten ball of rock. Hit that subscribe button, share your thoughts below, and let's keep exploring the together. Thanks for watching, and we'll see you in the next.